Next, we are going to see power spectral density or power spectrum. For that, we need some basic concept about Fourier transform. Fourier transform of x of t is given by Fourier transform of f of x of t, which is equal to x of omega, which is equal to integral minus infinite to plus infinite x of t e power I 2 pi omega t dt, or integral minus infinite to plus infinite x of t e power minus I omega t dt. And the inverse Fourier transform is x of t, which is equal to 1 by 2 pi integral minus infinite to plus infinite x of omega e power I 2 pi omega t d omega, or 1 by 2 pi integral minus infinite to plus infinite x of omega e power I omega t d omega. So normally we are using the second one for Fourier transform and inverse Fourier transform, right? Now we'll see power spectrum. The power spectrum is a representation of power of signal as a function of frequency. Normally we can see in the audio clippings, whenever you are doing recording, right? In the mobile also we are having the voice recording. You can see some lines are going up and down whenever you are speaking. That is called frequency. The height of each line is called amplitude, right? So the power signal becomes a frequency right there. So the power spectrum is the representation of the power of signals as a function of frequency. It shows how the power of a signal is distributed across the different frequency components, right? The power spectrum gives total power across discrete frequencies. It expressed in unit of power. We know power unit in watts versus frequency in hertz, right? Kilohertz, right? Some example, consider the sound of our voice. A wave form of our spoken word as a chart of loudness. Loudness is nothing but amplitude over the time. Whenever you are speaking very loudly, the line will go up. If you are speaking very low, then the line will be very short. You can see in the mobile voice recording, right? Over time. Example, voice recording in mobile. A voice recording for 15 seconds can be portrayed as a chart based on loudness perceived, measured in decibel. Sound always measured in decibel, we know. This chart of loudness by frequency, is a power spectral density chart. See, you can see that. Next, power spectral density. Power spectral density is a measure of power per unit frequency. So, like power spectrum, this is also the same. Power spectral density also the same, but we are measuring per unit frequency, not total frequency. It provides a density function that describes how the power of signal is distributed over frequency, normalized by the bandwidth, right? It is expressed in units of power per unit frequency, watts per hertz per kilohertz, right? Next, power spectral density function of a random process. The power spectral density of a continuous time, that is either wide sense stationary or strict sense stationary random process defined by the Fourier transform of its autocorrelation function. So, Fourier transform of a random process is give the power spectral density, right? So x of t is a stationary process either in the strict sense or wide sense with autocorrelation function r of tau. The Fourier transform of r of tau is called power density spectrum or power spectral density function of the random process x of t and is denoted by x of s of omega. That is the spectral density function s of omega, which is equal to Fourier transform of f of r of tau, which is equal to Fourier transform. We are taking Fourier transform of the r tau, the autocorrelation function r tau, integral minus infinite to plus infinite r tau e power minus I omega tau d tau, or s of f, which is equal to integral minus infinite to plus infinite r of tau e power minus I 2 pi f tau d tau. Normally we are using the first formula, right? Integral minus infinite to plus infinite r of tau e power minus I omega tau d tau. S of omega or s of f is given, then we can find r of tau by the inverse Fourier transform. While taking inverse Fourier transform to the power spectral density, we will get the autocorrelation function. The autocorrelation function r of tau, which is equal to inverse function of Fourier transform f inverse of s x of omega, which is equal to 1 by 2 pi integral minus infinite to plus infinite s x of omega e power I omega tau d omega, or 1 by 2 pi integral minus infinite to plus infinite s x of f e power I 2 pi f tau d f. We are using here the first formula only. Here s of x and r of x, sorry, s of omega r of tau form a Fourier transform pair. That means one is inverse Fourier transform of other, right? Fourier transform of r is s. Inverse Fourier transform of s is r. That is called Fourier transform pair. Next, properties of power density function. Property number 1, the value of the spectral density function at zero frequency is equal to the total area under the group of the autocorrelation function. We'll see the proof. We know s x of f, which is equal to integral minus infinite to plus infinite r x of tau e power minus I 2 pi f tau d tau. If f is equal to 0, so you will get s x of 0, which is equal to integral minus infinite to plus infinite r x of tau e power minus I 2 pi 0 tau d tau, which is nothing but integral minus infinite to plus infinite r x of tau d tau. So that what is the meaning of that? The integral minus infinite to plus infinite r of tau d tau is nothing but the area under the group of autocorrelation function. We know area of a function in the integration, the same formula. Instead of that function, you are having the autocorrelation function. Next, property 2. For a real random process x of t, s x of y, sorry, omega is an even function. What is the meaning even function? S x of omega, which is equal to s x of minus omega. So we'll see the proof. We know s x of omega, which is equal to integral minus infinite to plus infinite r x of tau e power minus I omega tau d tau. Equation number 1. Replace tau by minus tau in 1. So s x of omega, which is equal to integral infinite to minus infinite. Whenever you are changing the variable, limit also will change. Because when you are taking the limit tau is equal to minus infinite, minus tau becomes plus infinite, minus into minus plus. When you are taking tau is equal to minus infinite, plus infinite, then minus tau becomes minus infinite. So the limit will change, plus infinite to minus infinite, rxx of minus tau e power minus I omega into minus tau d of minus tau. So rxx of tau e power I omega t dt, we are taking the minus outside, right? Because d of minus tau, which is equal to minus d tau, we are taking that minus outside. And also we know the property from autocorrelation, rxx of tau, which is equal to rxx of minus tau. So yes, xx of omega, which is equal to minus infinite to plus infinite, because we are changing the limit, because minus lower limit plus infinite minus infinite. Now we are giving another minus, so minus into minus plus, we are changing the limit also, minus infinite to plus infinite. This is definite integral property, right? Minus infinite to plus infinite, rxx of tau e power I omega tau d tau. This is the equation number 2. Now replace omega by minus omega in equation number 1 again. Sxx of minus omega, which is equal to integral minus infinite to plus infinite, rxx of tau e power minus I minus omega tau d tau. That is equal to integral minus infinite to plus infinite, rxx of tau e power I omega tau d tau. That is equation number 3. See now from 2 and 3, sxx of omega from 2 is equal to sxx of minus omega from 3. Therefore, it is an even function. Now property third, it is obvious, sxx of omega always greater than or equal to 0 for all omega. Thanks. We'll see you in the next video.